We see that the odd expression we have 1 over 1 plus exponential, that can be converted to this. If you just do binomial expansion of that raised to power minus 1, the first two terms, you realize that this, your probability of occupancy reduces to this. And that is why that is important, because when we get to the issue of the actual so let me see, when we get to we said that your n is actually nc integral from I think is it nc, so sorry, gc of fe, and you now realize that you'll be talking that your n is something like nc exponential minus ef minus ec over kt. It is gotten from here. It is gotten from here. It's gotten from here. This probability of occupancy. So let's see another question. Calculate the energy in terms of kt and ef, at which the difference between the Boltzmann approximation and the Fermi-Dirac is 5% of the Fermi function. Do I really want to talk about that? No, not necessarily. So, but that's the concept that you need to know in the probability of occupancy. Yeah, we have talked about this. This is 6.25. This, we've done this in class. So that's the probability of occupancy, and again, it tells us that the density of states times the probability of occupancy will give us the concentration of carriers. Now we now look at the concentration of carriers. The concentration of carriers, they are talking about this, the bond diagram again. At thermal equilibrium, there's no doping, and this is at thermal equilibrium. This is our bond diagram at thermal equilibrium. So we are saying that we now have O's here, and we have electrons. So the concentration of the electrons here is what we call NC, the concentration of electrons in the conduction band. And then the concentration of holes here is what we call NV, which is the concentration of holes in the valence band. All right, so that we have this scenario. All right, so we have this concentration of electrons is this times this. Therefore, holes, I explained in class, it is this valence, and then it's 1 minus Fe, because if there's no hole, there's electron. If there's no electron, there's hole. All right, so we have this equation to ultimately give us this, the concentration of electrons is nc exponential this exponential. This equation is gotten from the Fermi-Dirac probability if you do the binomial expansion of the fraction, and then this nc is talking about the concentration that you have in the conduction band, and that's for electrons. For holes, it is nv, what we have in the valence band. So an example, assume Fermi energy level is 0.25 electron volts below the conduction band. The value of nc will be what? So I think they were trying to, so if that is the case, that is, we can have your concentration to be a function of a particular energy state. So in this case now, the probability of occupancy for an energy level that is 0.25 eV at 100 Kelvin, this is the probability of occupancy. This is the probability of occupancy. One thing you notice there is that because the temperature is very, very low, the probability too is very, very low. For the probability to be high, you need higher temperature, quite higher than 300 Kelvin. So this is how you get this, and then you use this formula to be able to now get the concentration of carriers at that energy level. To get the concentration of carriers at that energy